In this mini lesson, we're going to examine two methods for adding vectors, the geometric approach and the components approach. Although the latter is generally more useful, both methods have their advantages and both provide valuable insights into how vectors and vector addition work. But first, let's briefly review what it means to add vectors. Here's a graphical representation of two vectors, a and b, that we wish to add together. We understand well enough what adding numbers means, but what does it mean to add vectors? Well, just as adding two numbers gives a third number, adding two vectors gives a third vector, called the resultant. To find the resultant of a and b, move the vectors so that they're arranged with the tip of the first touching the tail of the second. Remember that a vector is defined entirely by its length and direction, and not by the location of either endpoint. So sliding a vector around doesn't turn it into a different vector as long as the length and orientation haven't changed. Once a and b are arranged tip to tail, as shown here, the resultant, a plus b, is the vector that goes from the tail of the first to the tip of the second. And just as with adding numbers, adding vectors doesn't depend on the order in which they're added. A plus b is the same vector as b plus a. Notice that the two black vectors shown here have the same length and point in the same direction. So they're the same vector. The fancy way of saying this is that vector addition is commutative. With this graphical representation in mind, we can develop two different methods for determining the resultant. That is, for determining the length and direction of a plus b. Let's do an example. A dog running through a field travels 40 meters in a direction 20 degrees north of east. She then changes directions and goes 75 meters along a path 50 degrees north of west. What is the dog's total displacement, both magnitude and direction? As always, it's a good idea to draw a picture. We represent the first leg of the dog's journey as a displacement vector of length 40, pointing in a direction 20 degrees counterclockwise from whatever direction we choose to call east, in this case horizontal and to the right. That's because north is counterclockwise from east, so the phrase north of east means counterclockwise from east. Next, we draw a displacement vector representing the second leg of the dog's journey. This time it's a vector of length 75, pointing 50 degrees clockwise from west. Since north is clockwise from west, north of west means clockwise from west. The total displacement vector goes from the starting point to the ending point. And since the vectors for each of the two legs of the journey are already arranged tip to tail, we see that the total displacement vector is just the resultant, or vector sum, of these two vectors. Notice that the three vectors form a triangle. This suggests a geometrical approach for finding the length and direction of the resultant. This blue triangle is the triangle formed by the three vectors. From the statement of the problem, we know the angles 20 degrees and 50 degrees that two of the sides make with the horizontal. And from basic geometry, we know that this angle is also 20 degrees. So now we know that this angle of the triangle is 70 degrees. That's 20 degrees plus 50 degrees. Okay, now we have enough information to calculate the length of the side corresponding to the total displacement vector and the angle theta shown here. And once we have theta, we know that the direction of the total displacement vector is theta plus 20 degrees north of east. But how are we going to use the information in this figure to find L and theta? Well, we can calculate L using the law of cosines. And once we have L, we can calculate theta using the law of sines. It's probably been a while since you learned about the law of cosines and the law of sines, so we better briefly review. Suppose you have a triangle, any triangle, with sides of length A, B, and C. Let's call the angle opposite A theta sub A, the angle opposite B theta sub B, and so on. The law of cosines lets us calculate the length of any of the sides of the triangle from the lengths of the other two and the opposite angle. For example, C is given in terms of A, B, and theta sub C by C equals the square root of A squared plus B squared minus 2AB cosine theta sub C. The law of cosines is often viewed as a generalization of the Pythagorean theorem to the case of non-right triangles. The law of sines tells us that the sine of any of the angles in the triangle divided by the length of the opposite side is the same for any pair, or more specifically, sine theta A divided by A is equal to sine theta sub B divided by B is equal to sine theta sub C divided by C. Okay, now back to our vector addition problem. For this triangle, we know the lengths of two sides, 40 meters and 75 meters, and the angle opposite the unknown side, which is 70 degrees. From this information, we compute L using the law of cosines. In particular, L is equal to the square root of 75 squared plus 40 squared minus 2 times 75 times 40 times cosine 70. This turns out to equal about 72 meters. Now that we know L and the angle opposite it, we can calculate theta, the angle opposite the 75 meter side, using the law of sines. In particular, we know that sine of theta divided by 75 has to equal sine of 70 degrees divided by L, or 71.92. Evaluating this tells us that sine theta is equal to 0.97990, or that theta is equal to 78.5 degrees. So theta plus 20 degrees is 98.5 degrees. Now back to the example to give the numbers meaning. What is the total displacement vector for the dog? Well, its length is 72 meters, and its direction is 98.5 degrees north of east. The geometric method of adding vectors is elegant and intuitive, but it can become rather cumbersome, especially if you're adding more than two vectors. The component method, however, is powerful, easy, once you learn how to do it, and scalable to any number of vectors you wish to add. Let's see how it works. Here is the illustration of our vector addition example, with a set of coordinate axes showing the east and north directions. Let's get rid of the numbers for now for clarity. We'll put them back in later. Now we need to resolve each of the vectors into components. That means expressing each one as the sum of two vectors, or 3 in 3 dimensions, one parallel to each coordinate axis. Here's how that works for the first vector. See how one of the components is parallel to the east direction and the other is parallel to north? And here are the components for the second vector. Notice that the component parallel to east actually points in the opposite direction, or west. All that means is that this component will be negative, since we've chosen east to be positive. Finally, here are the components for the resultant. But now notice something about the horizontal components. If we arrange the gray ones tip to tail, then their sum is equal to the pink one. In other words, the sum of the horizontal components of the two vectors being added is equal to the horizontal component of the resultant. This works for vertical components too. The sum of the vertical components of the two vectors being added is the vertical component of the resultant. So why is all this useful? Well, if we can determine the numerical values for the components of the two vectors being added, then we can easily get the components of the resultant. We do this with trigonometry, and let's see how that works. Here's the original figure with numbers added back in and with each vector resolved into components. Notice that each vector and its components form a right triangle with the vector as the hypotenuse. This is the setup we need to use trigonometry. Let's start with vertical components. For the 40-meter vector, the vertical component is the side opposite the 20-degree angle. Well, we know that opposite over hypotenuse is sine, so the length of this side is 40 times sine 20 degrees, or 13.68 meters. To get the vertical component of the 75-meter vector, we need to know one of the non-right angles of the right triangle formed by the vector and its components. From elementary geometry, we know that alternate interior angles of parallel lines are equal, or in particular, that this angle is 50 degrees. Now we see that the vertical component is the side opposite the 50-degree angle, so its length is 75 times sine of 50 degrees, or 57.45 meters. Now, the vertical component of the resultant is just the sum of the vertical components of the vectors being added. So its length is 57.45 plus 13.68, which equals 71.13 meters. Now let's move on to the horizontal components, starting with the 40-meter vector. This component is the side adjacent to the 20-degree angle. We know that adjacent over hypotenuse is cosine, so the length of this side is 40 cosine 20, which equals 37.59 meters. For the 75-meter vector, the horizontal component points west, which is the negative direction. So this component must be negative. Since it's the side adjacent to the 50-degree angle, its length is 75 cosine 50, and so the component is negative 75 cosine 50, or negative 48.21 meters. Adding the two horizontal components gives the horizontal component of the resultant. That is 37.59 plus negative 48.21 is equal to negative 10.62 meters. Now let's go back to the original problem, which was to find the length and direction of the resultant. Well, now we have the components of the resultant. How can we turn them into a length and direction? Well, we can use the Pythagorean theorem to get the length. L is equal to the square root of 71.13 squared plus negative 10.62 squared, which equals about 72 meters. We can get the angle theta, which gives the direction of the resultant relative to east, using trigonometry. Tangent theta is equal to the vertical component divided by the horizontal component, or in other words, opposite over adjacent. So that theta is equal to the inverse tangent, or arctangent, of 71.13 divided by negative 10.62, which equals about 98.5 degrees. One side point. Most calculators give inverse tangents in the range of negative 90 degrees to 90 degrees, and that's perfectly legal. But if you want your angle to be in the range of 0 to 180 degrees, and your calculator gives a negative number, all you have to do is add 180 to it. Summarizing the results of our calculations with components, we find that the dog's total displacement vector has length 72 meters and points 98.5 degrees north of east. This is exactly the same result we got using the geometrical method as we would expect. So which method should you use in adding vectors? Well, whichever one is more convenient to you. I suspect you'll find the component method to be more useful and systematic, and that'll certainly be true when adding more than two vectors. But each method has its merits, and each is worth knowing.